Okay, into lecture 2, we're going to continue with probabilities. Remember that what we had established was that any probability is a ratio, that's a fraction, and it equals the number of successes over the total possibilities. And if you put them as the number of possible successes over the number of possibilities that exist altogether, you get a fraction that goes no higher than 1 and no lower than 0. So it tends to be between 0 and 1 inclusive. The complement means everything else. So it's not like if I give someone a compliment, I'm telling them something about themselves. When we talk about the complement in statistics, and also here in probability, so I'll underline that as a vocab word. The simplest way to remember it is everything else. That's a general English definition of what a complement is. So if I say it's raining, is something I'm thinking about, everything else is it's not raining. Okay, it could be snowing, could be wind, whatever, but raining and everything else, so not raining. Left-handed, for a lot of people the complement of left-handed would be right-handed, but then not being left-handed means you could be right-handed, or, right, there's one in every crowd, someone wants to say, what about ambidextrous? But the complement means everything but or everything else compared to what we're looking at. So the probability of this is called the complement PE with a little tag on the E, right? It's like an apostrophe. Instead of meaning the probability of event E is the probability, which is what the P represents, of the complement of E. I'll get you an example. The probability of rain today is 0.3. I could call it 30% also. And if I were to tell it to you it's 30%, you might have an easier time telling me what the percent likelihood is of it not raining. But the probability of rain today equals 0.3. Therefore, we might say the probability, and it doesn't have to always be the letter E. If we're talking about rain, why not use the letter R, equals 0.3. Okay, got that? That's a statement leading into our question. Find the probability it will not rain. That's a complement. The complement to raining is not raining. And that would then be called the probability of raining's complement, or the complement of the probability of it raining, equals some number. Well, here's the thing. The probability of the complement of E is take 1, which represents your 100%, and subtract the probability of event E. Whatever letter you need to represent your event, there'll be a decimal value going in there, as high as 1 and as low as 0, and you'll take 1 minus that. So in extreme cases, 1 minus 0 gives you 1. Okay, so like the probability that Norwalk Community College is 20 stories high is 0. What's the probability that Norwalk Community College is not 20 stories high? Well, you put in the 0 for that, 1 minus 0, and it's 1, and that means it's guaranteed, as of right now anyway, Norwalk Community College, not 20 stories tall. Probability that Norwalk Community College has a parking lot, that's certain, right? Say, what's the probability Norwalk Community College does not have a parking lot? Well, you put your 1 in there for the probability of having the parking lot, 1 minus 1 gets you 0. The probability that Norwalk Community College has no parking lot, 0. But other things drop in there and get you numbers between 1 and 0 for the probability of the original event, as well as for its complement. Probability of raining was 0.3. So the probability of the complement of it raining, probability that it doesn't rain, is to take 0 minus 0.3 and get 0.7, which is saying if there's a 30% chance of rain today, there's a 70% chance of no rain today. And that's how we work with a complement. 1 minus the probability of something happens is the probability that does not happen. I just want to look at something called the multiplication principle. So that's the name of it, and that's what you do, and it's how you deal with independent events happening all at the same time. Independent events are special because they don't change each other. They're not relying on what happens in one case than happens in another. And so we'll look at that more closely later. But we're going to look at the multiplication principle. So the name is nice for it, and that's what it's called officially. So you know what to do. The definition of this principle is going to help you decide when to go ahead and use it. And it says for independent outcomes, as I had said, they don't depend on each other to decide how likely they are to occur. Happening, also important, together. The size of the sample space, and a sample space is all the possibilities of what might happen, is the product of all the sets sizes. What does that mean? Well, how many choices do you have for 1? How many choices do you have for 2? How many choices do you have for 3? Let's figure out what you can get by multiplying those together and creating, for example, a rectangle. If you multiply 2 numbers together, you get the area of a rectangle. And it will be that many rows times that many columns. That's how many square pieces you would get. But if you go to 3, we get into a third dimension, you start to build a rectangular box. You'll do length times width times height. You get the volume of that. And so you'll find out how many cubes you can fit in there. I don't have something that's a physical dimension to go beyond 3, so I can't tell you how to do something with the 4th dimension, which you may be familiar with if you've done anything in physics, which is time, because it wants to know how you're going left to right, how you're going up and down, right? How you're going front to back. That can help you find your location pretty much. GPS with a 3rd dimension for you to be off the ground. The 4th dimension would be time. We're not using time. It's not a physical dimension that we can measure that way, so we'll only go up to 3. But multiply them together. So the area of a rectangle, multiply length times width. The volume of a rectangular box, length times width, figure out the base, multiply it by how high it is. So I'm going to multiply. What does that mean? I have 12 colors of paint. Okay, I'm not going to rattle off 12 colors, but there probably could be a lot more. You go to a paint store for sure. And 3 textures. How many unique paints can I make? Let's have a lowercase of h here. So what you're going to do is textures I can handle. You can have flat, you can have semi-gloss, and you can have high gloss. Okay, those are 3 kinds of textures of what the paint might look like. There are more, but I'll just go with 3. Colors, there are 12. I'll start you off red, white, and blue, green, yellow, purple, orange, and so forth. So you have 12 of them. How many different paints can I make so that each one is different? Besides what the color is, how the light deals with it to reflect a certain color, how shiny is it? There are 3 ways it can be a certain level of shininess. Let's say we start with red. We can have flat, we can have semi-gloss, we can have high gloss. Then you go to blue, and the same thing, flat, semi-gloss, high gloss. Every color is going to have you doing that. So if you think of stacking 3 tall, even if you do it with pennies or something like that, 3 tall for each one of them, you're going to get 12 stacks of 3, and you're going to get 36. What was that? That was 12 times 3, and 36. And if I wrote the entire sample space up there, if green was one of my colors, somewhere in that sample space of all that might happen will be green 3 times. And then I say, but green high gloss once. There's 1 spot for the combination of it being green, which narrows it down from 36 down to 3, and then from those 3, 1 of them's high gloss, and 1 is the spot for it. So sample space is going to make up stuff like this, but multiplying these independent set sizes is going to tell you how many possible ways they can combine with each other when everything is possible. Every combination is allowed, so that you can have, a pink in flat paint. You can have a yellow in semi-gloss, but you can also have a yellow in gloss. All those would be up there among the 36, which we could do 3 tall and 12 across, and it would look like a rectangle. Count them up to 36, multiply 3 times 12, 12 times 3, 3 plus 3 plus 3, so you do it 12 times. You got 36. That's what we're going to find with our multiplication property. How about this? 3 appetizers. I should say that because, you know, smartphones and all that. 5 meals, which is your main course, 2 desserts. Okay. How many ways can you make these meals? It would be 3 ways. If you only had appetizers, you would have 3 choices. Okay, let's say we skipped the meal. We only had appetizers and desserts. This could be like A, B, C, and that could be 1 and 2. Watch me go. A with 1, A with 2, B with 1, B with 2, C with 1, C with 2, 6, and done. That would be if we didn't have the meal. And that would be 6, and that would be 3 times 2. But we have the appetizers. Then we say, well, what about the meal? That makes it go 5 times as many ways as just being 3 appetizers. So now if we didn't have dessert as an option, it would be 15. But because all 3 of these are involved, we find that that's 30. And if it's not February, right, you can get all the meal combinations done in a month. February, you know, if it's leap year, you get close, you miss by 1. Non-leap year, you miss by 2. But otherwise, you can get there. 31 days in a month, you'll have to have a repeat. What makes me sure if there are 31 days in a month and there are 30 ways to have the meal, why do I know that I have to have a repeat in there? That's something that's called the pigeonhole principle, which would be that pigeonholes are like these things you would stuff the birds in to get them in the cage in the right spot. And the pigeonhole principle is the name of it, that says if you have more stuff to put in holes than you have holes, they were doing that with pigeons, one of those spots is going to get more than one. It's a formal design as to why I can say, you know, if it's March, I'm going to have the same meal. If I go to that restaurant every day, try to get a different meal every time, by the last day I'm going to have to repeat myself. Here's one for you to try. As you know, with this being on the video, you could stop the video and try and get the answer yourself before I give it out to you. But I have outfits. My kids always laugh at me calling them outfits, but that's what goes on. Let's say that we're not worried about being too matchy or clashy, but any shirt can go with any pants that I have. If I have 4 shirts and 3 pairs of pants, okay. So sometimes I say the shirts are white, off-white, gray, and black, and the pants are just white, gray, and black. You make it all happen, right? They'll all work. But how many outfits can you make? And we would take the 4 times 3 and get 12. And 12 outfits you can make out of that. Now, if matching and clashing become an issue, there are still those ways you could put those outfits together if you had more colors or clashy colors or whatever, but 12 possibilities, and that creates what's called our sample space. So sample space helps us get what all the possibilities are. We try and line stuff up in an organized way, not just jumping all around and hoping we don't miss one and hoping we don't double hit one. It is about organizedly getting together what's possible for outcomes. And that's a really important part of some of the probability that we're going to do. If you're looking at the sample space, physically looking at a printed version or on the screen of your computer or smartphone, then you could, if you had enough time, count up all the ones that do what you're looking for and count up all the possibilities, make the fraction, the probability will be done. If you have your sample space in an organized fashion, it's usually a lot easier, quicker, and so forth, all good things, to get through the process because you don't have to count through all 36 ways 2 dice can be rolled, all 52 cards in a deck, because you say that, you know, oh, here's where all the 8s are, they line up. Here's where all the spades are, they all line up. Whatever it is, you can get that done because your sample space is done in a neat order. Factorials are a certain type of product. The product is done by multiplying, and what factorial is, that's called n factorial, and it's not someone enthusiastic about n. In math, it means we want to start with n, which has to be a positive integer, or it could be 0, so I could actually say it's a whole number. 0 is one of the whole numbers. But it's not having a fraction, it's not negative. in front of that. And what we want to do is make a product of all the numbers from that on down. We're making sure that we stick with our integers that are positive as we do that. So I want to give you an informal definition. It is n times each smaller positive integer. So it's best to just keep them in line and drop them on down. So here's how that looks. N factorial equals, in general, but this might be too big to write in some cases, n minus 1, n minus 2. Works okay if your number is at least as big as 3. Dot, 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 follow the pattern until you hit 3, 2, 1. Now this works great, okay, if you have a number that is 6 or bigger, because it would be 6, that's 5, that's 4, and then 3, 2, 1. And so 6 factorial fits perfectly. You can't say this whole pattern holds up if your number gets to be smaller than 6, but you can do what that says. Say I wanted to get 4 factorial. Start with 4 and just go 4, 3, 2, 1, or 5, 4, 3, 2, 1 if it's 5, and take yourself down to 1. Hitting every single integer between your number and 1. Stop it when you hit the 1. If your number is 1, then you're there, and you get 1. And there's a definition, and we'll look at why this is. 0 factorial sure seems like it would be 0, but what we do with factorials determines that 0 factorial actually needs to be having the value of 1. And what factorials do is they help us count possibilities of outcomes in sample sets where the numbers are dropping because we're taking something out of what we're drawing from, making it a smaller number. So that if we started with something like, let me get you a couple of these to work out. 3 factorial. Start at 3, go 2 to 1. 3 times 2 is 6, times 1 is 6, and you're done. Right? Take it to 5 factorial. Now that's 5 times 4 times 3 times 2 times 1 for sure, which will get you 5 times 4 for 20. 20 times 3 get you 60, times 2 is 120, times 1 you get 120. Or 5 times 4 is 20. And that's 3 factorial. So you take your 20 times 6, 120. So you may be familiar after you work with them a little bit that, okay, 0 factorial is defined as 1. 1 factorial is done when it starts as 1. 2 times 1 for 2 factorial is 2. 2 times 3 gets you 6. 6 times 4 gets you 24. 5 times 24, it's going to ratchet your way up through there. So, I hope the colors work out pretty well on this. Let me get the dice. No, that's the holes. Yeah, nice. I want to show you 3 factorial. I want a pretty clear difference in the dice colors. I got a green one, I got a light purple one, and I hope I got the clear cut. Yes, black one. Okay. There we go. What factorials do is they count the ways we can order a set number of items. Okay? So you're looking at this and you're reading from left to right. I'm looking at the back of them, I'm seeing them different. Okay? What we have here is green. I'll call that purple and black, right? It's violet, but anyway, green, purple, black. If you look at the way you would read that. Now, what happens? If I want to come up with a different order for those, I can still have green be first, but I can have green, black, purple. That's because I had green coming first. The ones that had that were green, purple, black, and green, black, purple. Now that's it. That's what I can do if I want green to be first. So now I said, you know what? Let's put black first. All right, I got black, green, purple. That's the way I did it this way. It's fine. Black, green, purple is one of them. Black, green, purple is still standing. Still want black first, so I want black, purple, green. Black, purple, green is a possible way those can be ordered. It's different than ones we've had so far. Now you can slow down or stop the tape if you want to think about, we've got 4 of them, but there are still possibilities. I did a couple where green was first, I did a couple where black was first. Think about what else could be first. Not black, not green, those have already had their chance. The answer's purple. As I put purple first, one of the things I come up with is purple, black, green. Is there anything else that can happen if purple is first? The answer is yes, purple, green, black. I did everything I could with green being first, so no more of those. Then did everything I could with black being first, no more of those. Went out and did everything with green being first, and there's nothing else that can be first because I've used them all first. I got 6. This is the concept of the multiplying by numbers that are smaller than you. The first block can be one of a certain number, and then when one of them is taken out, there aren't as many to be there the next time, and we're going to use the multiplication principle. So I have green, purple, and blue, and I put them behind my back. Right? You might guess which one it's going to be, but your guessing is not what makes you good. It's, do you mathematically see what's supposed to come out of here? So don't worry about what your guess is, but here's what I came up with. I drew out the black one first. How many might have come out of that to get there? And that was 3. Now we're determined to use the multiplication principle, so black is there. Black is out of behind me. It is here on the desk, or we'll see if we can get a nice balance of it over there. Black is there. I'm going to put the 1 up, right? I guess that's why. Black died. Kind of hard to tell in this darkness, but black came up first on that one problem. Go back to ones that are still available. You can hear them maybe clicking back there. There's a reason, because there are some back there, but not 3. Black one's not there anymore. There are now 2, which is why one of 2 is going to come out the next time. Which one? Your guess is as good or bad as mine, but you know what? It's not going to be black. It'll be purple or green. It happens that when I draw this one, it's purple. Second one that time was purple. It's one of 2 choices. Now I go take what's still here, and I put that behind my back. And as hard as I might jiggle and all that, it's not going to make any noise. Because I had 3, black came out, I had 2. Purple came out of the 2, I have 1. I have 1 back there, it's not making any noise. What color's behind me? We had black, purple, and green. Black is now already parked. Purple is parked. You know what's back there, it's green. Hey, I got that one right. How many possibilities were there for that one? 1. So 3 times 2 times 1 justifies why we used 3 factorial for this. We took how many there are. A factorial of n determines how many different orders can be set, putting, I'm going to put the word all in parentheses here, but it is helpful later, n items in a row. The row is not a circle, right? The row has a beginning and an end. They were all different colors. I didn't have 2 blues and 3 reds and stuff like that, but they're different items. And how many different orders can I get? And there's the demonstration of what goes on with 3. If I had 4 dice, okay, if this, that's purple again, nice. Red one were back there the whole time, I would have started with 4. I would have begun with a 4, and 1 of 4 would be the first one, no matter which one it would be. 3 after, then 2, then 1, and I would have gotten 4 times what that got for me. I would have had 24. And that's what a factorial is to do. Now there are ways to get factorials on your calculator, as long as you have a scientific calculator. Most of them will have a key that looks like this. I'll make it look a little chiclety, right? A little bit like a box, but it's got to have an exclamation point on it. What you do is you put the number in, hit the exclamation point, and then you hit equals, and it puts to work that factorial, which would be good when we're working on some formulas if that's the kind of calculator you have. Now, with the graphing calculator, we have a little bit more that it can do for us. And so I'm going to demonstrate that as well. If you don't have the graphing calculator, you can speed through it till I put this calculator down. But if you do, let's go find our 5 factorial. Okay? What we're going to do is you need to have some familiarity with it. I'm not telling you to memorize the keys, but you can play this back and write it down if you have the graphing calculator. Put in the number 5. What you're trying to take the factorial of, put that down. Now, what we want to do is we want to do some math, so we hit the key called math. That creates, across the top, a menu of options for us. There's a math key, a number key, a complex key, and a probability key. PRB is for probability. We're dealing with probability now, so we get our arrows to move us over to the PRB key. I'll tell you what, it loops around the back. What does that mean? If you're sitting on math and you want to get to the far end, you can click to the left, it'll pop up on PRB. But you want, as you click across, you'll notice that what is offered to you in the menu changes with each top of the menu you select. Get yourself to PRB, and you'll see the 4th one down there, at least on this one. Maybe yours is different. Maybe you got an old one or a newer one, and so maybe it didn't stick to 4 being there. So I don't want to tell everyone to hit math 4 and write that down, memorize it, put it on your note card. No. Know that we're going to math, we're going for probability. So we get to math, we get to probability, and we seek out where the factorial key is. So this one had me go down to the 4. I could have also hit right on that time while it was looking for what you want, the 4. I hit enter. Now what that does is it establishes, here's your 5 factorial. And it didn't get my answer yet, because it's now for me to look and say, yeah, that's what I want, and now I hit enter and the math gets done, it's 120. Now, you want to quickly get something, try 9 factorial. Clear, put in 9, math. You want to turn it off and try it yourself, go ahead, or follow through me. Get to PRB, get to where the factorial key is, and hit enter. 362880. That's how quickly it can do a factorial, as long as it can handle what you've got. There are limitations for its ability to fully write out the probability, the factorial. For example, if you wanted to try 100 factorial, 100 math probability, get down to the factorial, okay, and then you hit enter, and it says overflow. That means it goes past what your calculator can get for you, not just because it doesn't have a big enough screen to show all the digits, but also because it only goes up to 10 to the 99th power. Right? It goes with 1 with 99 zeros after it. It doesn't have a 3rd digit for scientific notation, so it can overflow. So if you're stuck doing that, you might have a problem whenever you'd have to have part of your work include the computation of a big number to the factorial. So keep that in mind. But factorial keys are available. Finding it by hand is possible. These are things we can do. So I will be done with the graphing calculator now, and you can come back to what we're going to work on.